Hi.
Hi. Hi.
Welcome to the session for filtering. I'm the chair of this session. My name is Fodio Stavro. And together we will see 5 video presentations. So let's wait for other people to connect.
Good morning.
Good morning, Oleg.
We are ready.
Yes, I think we are.
Okay. As you said, you will present the first speaker, then I present the second one, and so on.
So you guys still having hangover from yesterday?
Okay, we have the first speaker.
So let's wait until 10:30, which is the time that is supposed to start this technical session.
Okay.
So I guess all the involved participants are connected to this session. So I suggest to just briefly explain the rules as the session goes on. The cameras will be on only for myself and co-chair and
Moderator.
And the moderator, yes. And if you have to ask a question, then you raise your hand through your computer and you ask a question or make a comment on the chat. If you don't do this, please keep your microphones mute. Also, if you want to say something without writing, but in real time, then I suggest to activate your web cameras.
Okay.
So that's it, basically, nothing more, nothing less. Let's wait for another 5 minutes before we start, just to keep track of the schedule.
Join our special session for a talk by Professor Duarte Antunes on teaching MATLAB with live scripts. MathWorks has various resources for online teaching. MATLAB Tech Talks are educational videos that you can leverage to supplement your teaching of engineering concepts. Feel free to check out our free video collection by visiting the link or scanning the QR code. With MATLAB Live Editor, you can create interactive exercises where descriptive text and executable code are combined in a single document. Using MATLAB Online, students can run these exercises from any web browser without needing to install MATLAB. You can save instruction time by leveraging the free interactive tutorials on MATLAB, Simulink, machine learning, deep learning, and Stateflow. For more information on available resources, please check out our website.
Okay, we start with our first video presentation. The first presenter is Kailai Lee with the work entitled Green-Based Quaternion Filter for SO3 Estimation.
In this talk, we propose a novel grid-based quaternion filter for SO3 estimation. My name is Kailai Lee. I'm a research assistant at the Intelligent Sensor Actuator Systems Lab at Karlsruhe Institute of Technology. This work is done together with my colleague Florian Pfaff and Uwe Hannebeck. Representing spatial orientations can be done with multiple approaches. One of the most popular approaches are Euler angles. However, as shown in this animation, they have the typical issue that is the gimbal lock. When two axes are aligned with each other, 1 degree of freedom is lost. This problem can be overcome via overparameterization with the rotation matrices. However, they introduce a large degree of redundancy, with 9 elements used to represent the 3 degrees of freedom, which leads to higher memory consumption and potential numerical instabilities. As a reparameterization of the axis angle representation, unit quaternions can be formulated as 4-dimensional vectors, resulting in only 1 degree of redundancy and no ambiguities. A quaternion is composed by a rotation angle theta around the axis u, which is unit vector. Thus, it naturally locates on the 3-dimensional unit hypersphere. Moreover, an antipodal symmetric quaternion indicates rotation of 2 pi minus theta around an axis of opposite direction. Therefore, they denote the same rotation. When modeling the uncertainty of unit quaternions, the nonlinear hyperspherical structure should be considered. Traditional ways rely on linearization on the manifold based on the assumption of local perturbation. This can be violated when there exists large uncertainty or fast motion. For direct on-manifold stochastic modeling, one can exploit distributions from directional statistics. One popular choice is to use the Bingham distribution, shown in this picture, which inherently has a density of antipodal symmetry. Based on the Bingham distribution, a nonlinear filtering approach has been proposed for rigid body motion estimation. As shown in this video, we have presented in our previous work how this distribution can be deployed for stereo visual odometry. By using feature points extracted from the stereo image stream, our system is able to estimate eagle motion accurately in an unknown environment. The Bingham distribution does not have a closed-form solution for computing the normalization constant of the density. Therefore, the Bingham-based filters usually rely on schemes of sampling and matching up to the second-order moment. As the random samples lack efficiency and cannot reproduce the results, deterministic sampling approaches are proposed. For instance, one can take the idea of uncentered transform, namely an approximation up to the second-order moment, to have one pair of samples on each principal direction. To approximate higher shape information, sampling approaches generating arbitrary numbers of samples were also done. First proposed on principal directions, then on the whole hyperspherical domain. The limitation of parametric approach is quite obvious. There needs to be a pre-assumed probability density function of parametric form, which can be easily violated by an underlying distribution of arbitrary shape. Also, the sampling scheme itself involves optimization, which lacks efficiency for online estimation. For non-parametric modeling approaches, the particle filter lacks efficiency. A grid-based filter was proposed first on the circular domain, where an arbitrary distribution is discretized by grid points with uniform intervals. In this work, we take this idea and propose a grid-based filter for the hypersphere. A grid is therefore needed not only on the one-dimensional circle, but also for higher dimensions. Also, the grid-based stochastic modeling and filtering scheme need to be adaptive to the hyperspherical geometry. For this, we deploy a grid on the hypersphere, with each grid point beta supporting one component of a Dirac mixture density. The weight of each Dirac component is then the underlying density evaluated at each grid point. How to get a grid? An intuitive idea is to get grid points by equally partitioning the hyperspherical surface, as shown in this picture. The approach, denoted as SEP, is spherical eco-partitioning. We propose, however, a mode-centric grid. This is done by first discretizing the tangent plane at the mode M, layer-wise by a range of radii, then mapping the untangent plane grid points back to the hypersphere via exponential map. In this example, we can see a synthesized multimodal distribution on the hypersphere, on the sphere, and we further model the uncertainty by using the MCG, the mode-centric grid, and the grid from ICP, the spherical eco-partitioning. The MCG-based modeling then gives a higher resolution in the vicinity of the mode. It allows multimodality and gives more detailed representation in the area of large gradient. For highly nonlinear estimation tasks, this brings a better trade-off between the tracking accuracy and computational cost compared with the SCP. We further showed MCG-based modeling of the same Bingham distribution on the hypersphere S3 with different resolutions. We draw the underlying distribution using small red dots and denote the grid points with a blue circle. And the size of the blue circle indicates the weight on each grid point. The proposed grid-based quaternion filter is deployed for the following setup. The system state xk, which is the quaternion, belongs to the hypersphere S3, and the system noise W belongs to its own domain. The transition model A propagates the state to next time step with noise term. And the measurement model is also of generic form with set and V denoting the measurement and measurement noise. The prior density can then be represented by grid Dirac mixture with propagated weighting factors, and posterior is obtained by updating the grid weights with the likelihood evaluated at each grid point. Two side effects occur when propagating grid points. First, the hyperspherical grid is no longer centralized at mode, and the propagated points almost surely do not land on the grid again. For the first effect, we transport the grid from the old mode to the current one via the Hamilton product, as it essentially denotes SO4 rotation on the S3 hypersphere. To solve the second one, we can reallocate the propagated weights among the nearest grid points. As evaluation, we set up a system model with a noise term synthesized by a van Mises distributed rotation angle and a van Mises-Fisher distributed rotation axis. The measurement model rotates initialized points according to the quaternion state and have an additive noise term that is Gaussian distributed. We compare the proposed grid-based quaternion filter with other state-of-the-art directional estimation approaches based on the Bingham distribution under different noise levels. Here, a smaller c for the covariance of the Gaussian distribution indicates lower uncertainty and leads to more peaky likelihood functions. We have 100 Monte Carlo runs with 50 steps each. We first show a segment of a typical run to show the effectiveness of our approach. At each step, weighted grid points of the posterior are also depicted for showing the uncertainty. And the proposed approach gives the best tracking accuracy and efficiency under all noise levels, especially for the low noise level on the right-hand side. The other Bingham filters suffer from the sample degeneration issue due to the peaky likelihood and thus totally failed for all runs. A same filtering scheme using the SCP-based grade is also tested. However, the SCP-based approach with 5,000 grid points still performs slightly worse and is much slower than the MCG-based filter with around 1,600 grid points. This is not surprising, as MCG has a more efficient modeling of the underlying uncertainty. Further, increasing the grid resolution improves the tracking accuracy and demands more runtime as well. To sum up, we propose a mode-centric based grade to model arbitrary density on the hypersphere. This is further used for the grid-based filtering approach for nonlinear quaternion estimation, which shows superior performance compared with conventional approaches. Further potential of the discrete quaternion filter can still be exploited. Real-world experiments can be done for further evaluating the proposed quaternion filter. The state space can be extended to other manifolds, for example, products of hyperspheres, or the manifold representing the 6th degree of freedom rigid body motions. Here is a list of cited publications, and thank you for your attention.
Let's thank the presenter. Do we have any questions? Yes, Andrei
Matorin.
Yes, and can you please open your camera and ask the question?
Good day, everyone. My question is as follows. As I understand, you estimate the rotation of rigid body, but in example, you show up the positioning error. So how it coincides with each other? Do you mean that object moving on Earth sphere or something else?
Okay, thank you for your question. I think in the simulation, in the evaluation case, we have the system model as a rotation that is manipulated by a quaternion state. And for the measurement model, that is basically a measurement of the current position after the rotation done by the quaternion. So it's so the state we are estimating is just quaternion state, and just in the error term, we are comparing the position measurement given by the estimated quaternion and compare with the ground truth. Because in that case, we do not we didn't ignore any degree of freedom. It's still a three degree of freedom from the estimated quaternion to the measurement space. So it's not rigid body motion, but it's only the rigid rotation. That is the thing we are estimating. Yeah.
So it's rotation, and how you calculate the RMSE in this case?
Sorry?
How did you calculate the RMSE?
How did you calculate? Well,
There are different measures of error on the sphere, and you could use many of them.
Well, I think the error term on the sphere, you could use the arc length. That's definitely possible. Although this is a hypersphere, this is a S3 hypersphere, but you can still calculate geodesic. That is the arc length on the hypersphere. Basically, you have your ground truth that stays one quaternion, and you have your estimate quaternion. Both of them are on the hypersphere, and you can compare them by calculating the geodesic between them. That is arc length. So you can calculate as a you could do the inner product of these two quaternions and calculate the error term as an angular degree out of it.
Okay.
So it's basically the arccoside of the dot product of the two vectors.
Yeah.
That's the error term.
Yeah.
Okay.
So do we have any other questions? So perhaps I should ask one silly question myself. So what's the computational complexity of your approach? Did you check?
Well, it depends on, first of all, the resolution of the grade. So first of all, the dimensionality of the hypersphere. In our case, this is S3 hypersphere. This is in a unit sphere in the four-dimensional space, Euclidean space. And for getting the grid, we are discretizing, first of all, the tangent plane of the hypersphere with the resolution of the radii and also resolution of, so basically we first have, for example, if we have M grid points on the hypersphere, then each time we are doing the prediction step, we have to calculate, we have to allocate our propagated sample around the neighboring grid points. And in that case, you could actually manually define in which scale of the neighborhood would you allocate your propagated grid points. For example, you could have the surrounding 8 points and allocate the weight into the neighboring 8 points, and then in the update step, you just do the reweighting for each of the grade. So it depends on the resolution of the grid points, and also the allocating. When you are doing the allocation in the prediction step, depends on how many neighboring points are you allocating the weight, the propagated points. Yeah.
Okay, thanks. Yeah. So Andre has another question because I see his hand.
Yes, you said that you place your points in the vicinity of the probability density mode.
Yes.
And you also say that you can deal with multimodal distributions. Yes. What would be if the distribution, for example, has two modes and they're somewhat separated from each other?
Well, I think, first of all, I think this is a very good question, because we also consider it as a potential direction for this grid-based quaternion filter, because right now we are having a grid that has a single mode. Yeah. So we have the higher resolution at the vicinity of the mode, and to calculate this mode on the hypersphere, you can use some you could averaging the grid quaternion points, or you can use some other approach to calculate just one single mode, and you put the center of the grid at the mode of this density on the hypersphere. Yeah, and in that case, maybe you would ignore somewhere that also has a higher density of on the hypersphere. So this might be a downside of this approach. But later we actually are thinking, for example, to have adaptive grid points on the hypersphere. So for example, if you have several modes that has a higher gradient, and you could actually have several places where the grid has a higher resolution. Yeah. And somewhere else, when you do not have a large gradient, then you could actually have a very sparse grid. That might be a good potential direction in the future. Yeah.
Okay, thank you for your answer.
Maybe I should add that actually you can have it very good bimodal. I mean, if you have it on the other side of the sphere, I mean, unimodal may be a bit confusing because you can capture two modes at two opposite points on the hypersphere, because that's very important for quaternions, because they are a double covering of the space, because Q and minus Q describe the same rotation. And actually, if you're lucky and the grid has some points there, it can capture still some other modes. And in the presentation, we've also mentioned the SEP grid, and this is homogeneous on the sphere, and this inherently allows for multiple modes.
So guys, I should interrupt you because the time has elapsed. So let's proceed to the next presenter. Oleg, will you?
Okay, thank you.
Yeah.
Good day, everybody. My name is Oleg Stepanov. I am co-chair of the session. And now I would like to give the floor to the second speaker, Venkata Ginathan Poliseti. You are welcome.
The title of current talk is Convergence of Particle Filter for Output Feedback Control. The outline of the talk is as shown, which includes the following 8 sections. In the current work, Convergence of Particle Filter for Output Feedback Control is studied with the following dynamics, where input is a function of previous outputs. Here we assume X0 has a known distribution. All the noises, state and observation noises in initial state, are mutually independent random variables. And the state noise and measurement noise have densities PWT, PVT respectively. When output feedback control is used, we obtain these equations. Here we can note that y0 to t depends on x0 to t. xt plus 1 will depend on past data, which thereby creates a dependency between xt plus 1 and xt minus k for k greater than or equal to 0. Further, the process xt is not independent of the process vt, and the Markov property is not valid. In literature, existing convergence results for particle filters are given only for the case of a Markov process, and the convergence is established under the assumptions that xt being a Markov process and xt is independent of process vt, and transition kernel S follows Feller property. Other authors like Dawes et al. And Del Moral et al. Presented results on convergence in Markov case. In this paper, it is proved that the recursive equations relating the two prior and posterior measures which remain valid in output feedback case. And using these recursive equations, we further prove that the random measures produced by particle filter converge to two prior and posterior measures. The notations in the current work are as given. Lowercase letters, example x, are used for random variables and functions. X tilde denotes the values assumed by the random variable x. P of dx tilde denotes the probability measure induced by the random variable x. P of dx tilde dy tilde denotes the joint probability measure induced by the random variables x and y. B of R and x denotes the Borel-Sigma algebra on R and x. In this paper, we first define the extended transition kernel denoted by k subscript t minus 1 as the conditional probability of xt given xt minus 1 and y0 to t minus 1. Further, we define for any bounded measurable function b, kb represents integral of b with respect to conditional probability given by kt minus 1. The goal of particle filter is to approximate the prior and posterior measures, where prior measure is conditional probability of xt given past data y0 to t minus 1, and the posterior measure is conditional probability of xt given the data until current time t. In general, there are no direct expressions for these measures. Here we define notation for another integration. The pi t minus 1 kt minus 1 is defined as a new measure by integrating conditional property kt minus 1 with respect to posterior measure pi t minus 1. Similarly, we define other integrals. For any function b, the integral with respect to prior measure and posterior measure and the integral with respect to the measure defined above are all defined as shown. We note that integral of b with respect to pi k is a two-step integral. That is, integrating b with respect to measure pi k is equal to integrating b with respect to k first and then integrating kb with respect to pi next. In the current work, two types of convergence of random measures are considered: mu a and mu b, finite random measures. The measures mu n converge to mu weakly, denoted as mu n to mu, if expectation of mu a and b minus mu b tends to 0 as n tends to infinity for all b. The measures mu n converge to mu strongly, denoted as mu n strongly converging to mu, if mu n b converges to mu b as n tends to infinity for all p. Now coming to recursive equations for Markovian case, Crisan et al. Has shown that conditional expectation of a function of xt given past data can be written in terms of posterior Markov transition kernel in that function. Here we show some steps in proof to motivate our results. The proof uses properties of conditional expectation. It can be noted that when the process is not Markovian, the second and third step equalities do not apply. In second step, independence of xt, vt is used, and third step, Markov property is used. But in output feedback case, both of them are not applicable. So instead of using Markov transition kernel, which does not contain effect of data, we extend this and define the extended transition kernel by even conditioning on data. Now coming to recursive equations for output feedback control case. In this paper, using extended transition kernel, we prove lemma 2, which is integrating a function with respect to prior measure is equal to integrating that function with respect to measure pi k. The proof of lemma 2 uses Montan class theorem. Now, by defining h as density function of measurement noise, we can show that Radon-Nikodym derivative of posterior with respect to prior as function of h and divided by integral of h with respect to prior in lemma 3. And the proof of lemma 3 follows similar techniques as given in Crisan et al. Now we briefly discuss the steps in particle filtering algorithm. It is assumed that the observations are fixed to y tilde 0 to t, so that lemma 2 and lemma 3 are valid for this output sequence. And it is to be noted that both those results are valid only on a set of output sequences with probability 1 with respect to the measure induced by sequence of random variables y0 to t. The particle filter algorithm starts with initial samples from initial distribution and defines an empirical measure pi 0n based on the initial samples using the approximation shown. The particles or samples at time t-1 are passed through state equation to create particles that represent the prior measure, which is defined empirically using this approximation denoted by PTN. In the third step, each of the particles from previous step is given a weight depending on the likelihood of those particles with respect to observed output data. And then we defined a weighted posterior measure pi bar Tn with those weights using this approximation. Next, we would like to obtain an equally weighted empirical measure. So for this purpose, a resampling procedure is carried out to give resampled particles. And then we get an equally weighted posterior measure by Tn using this approximation. Now here we summarize the variables used in convergence proof of particle filtering algorithm. Y tilde 0 to t is a fixed sequence of observations. Ptn, pi bar Tn, pi Tn are the random probability measures obtained from particle filter algorithm. Pt y tilde 0 to t minus 1, pi t y tilde 0 to t are deterministic probability measures. It is shown that Ptn converges to Pt y tilde 0 to t minus 1 and pi Tn converges to pi t y tilde 0 to t, both in weak and strong sense. The proofs depend on lemma 2 obtained for the non-Markovian case in our work. First, we show weak convergence, which is proved in 2 steps. In the first theorem, we show equivalence of weak convergences to the equivalence of convergences of these 3 measures. Then in theorem 2, we show that these convergences do happen. And therefore, we claim that empirical measures given by particle filter converge to true measures. The proofs of theorem 1 and theorem 2 uses approach as in Crisan et al., but also use the concepts of extended transition kernel, lemma 2 and lemma 3. We further prove strong convergence. In most practical applications, only one string of particles are ever maintained, and hence strong convergence is desirable. Theorem 3 states that for all t between 0 to t, the empirical measures given by PF algorithm converge to true prior and posterior measures. Again, the proof of theorem 3 uses approach as in Crisan et al., but uses concepts of external transition kernel, lemma 2 and lemma 3. The theorem 2 and 3 show the convergence of empirical measures obtained from particle filter algorithm when the number of particles tend to infinity. In the current work, we take a standard nonlinear dynamical system with an additional input term as shown. And here the input dependence on output is considered to be ut as summation of outputs till time t. We perform 2 simulations with different q r values, and the number of particles in both simulations are 100. Here is the result for the case when q is equal to 5 and r is equal to 1. And here is the result for the case when q is equal to 5 and r is equal to 5. We see that in both the cases, the estimates are in agreement with true states. And also our current example demonstrates that for a reasonably small value of n, the particle filter is able to provide accurate estimates. So in conclusion, when the inputs of dynamic system depend on the previous outputs, the state dynamics becomes non-Markovian. In this work, it is shown that the Bayes recursive equations relating the true prior and posterior measures will still be valid in this non-Markovian setting. Also, it is proved that random empirical measures converge to true prior and posterior measures, both in the weak and strong sense. And simulations for output feedback control of a nonlinear dynamical system are presented, and it's also observed that The estimated states from the particle filter are close to true states. Thank you for your kind attention.
Okay, thank you very much for your presentation. First of all, I'm sorry for incorrect speaker presentation, because in the slide we can see another name of the speaker, Phanidra Jampana. Is it correct?
Actually, the name of the speaker is Gautam Polisetti. I'm the last author.
Okay. And now the time for question. Are there any question? Okay, I have a question. What can you say about the accuracy of this method? How this accuracy dependent of the number of the particle?
The number of particles, as the number of particles increased, we still see that convergence. I mean, we still see not the convergence, we still see that estimation is happening.
Okay.
Actually, this paper, we were more focused on proving convergence as these particles go to infinity. So we don't currently have the error, any estimate for the error for a finite n, for a finite value of the number of particles.
Okay. Are there any question? Okay. I ask you the second question. What can you say about practical application of the method? Some practical problems where you can use this approach and this method.
Yeah, so essentially the idea is for designing feedback controllers, especially for nonlinear systems where state information is important. So maybe this approach we are thinking of using it for designing such controllers, but right now it is still we haven't fully explored that part.
Okay, and we have the question from Vasiliev Vladimir. First question we discussed, and the second question is in the examples, estimates are shown for only one implementation of the algorithms. It is interesting to know some more complex accuracy characteristics, such as root mean square error, for example, for this algorithm. For many runs of Monte Carlo simulation.
Yes, we agree. I think it would have been also good to show the actual density functions, the distributions. But in this paper, due to lack of space, we only gave one simulation.
Okay. Are there any question? Some comment? We have 1-2 minutes before the next presentation.
I just want to add that we were mostly looking at the theoretical properties. So we didn't focus much on the numerical part, and we were limited by the page length to add all those.
Okay. Because we have no comment and question, I would like to give the floor to my colleague, my first chairman, Fotios. Welcome.
Thank you for your nice words, Oleg. So it happens that the next presenter is, I guess, a colleague of Oleg, because they are collaborators on this paper. The paper is entitled Application of Polynomial Filtering Algorithms to Nonlinear Discrete Dynamical Systems in Navigation Data Processing. The presenter is Yulia Litvinenko.
Good morning, dear colleagues. I'm going to start our presentation, Application of Polynomial Filtering Algorithms to Nonlinear Discrete Dynamical System in Navigation Data Processing. Here on the slide, you can see the context of my presentation. After a short introduction, I will talk about problem statement. Then I will talk about suboptimal algorithms, and first of all about polynomial filtering method. Then I will discuss the procedures which we use to estimate the efficiency of the filtering algorithm. And finally, I will give you some examples. One of the features of the navigation data processing is that we need to solve estimation problem with nonlinearities in the equations for state vector and measurements. The example of such a problem statement you can see here on this slide. The problem can be solved by using nonlinear filtering methods in the framework of the Bayesian approach. It is well known that the optimal in-mean square sense estimate of X and the corresponding covariance matrix are defined in the following formulas, where F, X, Y is a posteriori probability density function that can be calculated by following a recursive relation. However, the calculation of such conditional expectation, it is a challenge from the computational viewpoint, yet it usually couldn't be realized in a real-time mode, which is important for navigation data processing. So, to solve this problem, we can use different types of suboptimal algorithms, which provide accuracy close to the accuracy of the optimal algorithms. The various groups of suboptimal algorithms are based on different methods of approximation of a probability density function. We can distinguish two main groups of such algorithms. The first group is based on a Gaussian approximation. These are so-called Kalman-type algorithms, which include extended Kalman filter, the filter with local iterations, ascending Kalman filter, and others. The second group of algorithms is based on the reconstruction of the probability density function. In this group, the best-known algorithms are the mass point method and various modifications of the Monte Carlo method. Using this approach, we can design algorithms that provide accuracy close to the optimal algorithms. However, such algorithms still require significant computational costs. To synthesize algorithms which do not require a large amount of computation, it is necessary to take into account the specific feature of the problem being solved. And so now I'm going to discuss the problem statement. It was previously shown that the method of the polynomial filtering have been very successful in solving estimation problem with a polynomial nonlinearity in measurement equations. In this way, we propose to consider the possibility of using such algorithm for solving problem, the feature of which is shown in this slide. As we can see here, the state vector includes two vectors, x and theta. The equation 1 for vector x is nonlinear, and this equation is dependent on unknown parameter theta, which described by following a linear equation. The model for measurement is linear. And a nonlinear function psi is a polynomial of second order relative to x and theta. In particular, this situation is typical for identification problem, which requires both estimation of the state vector and the estimation of the model parameters. Let us consider the composite vector x tilde, which includes vector x and vector theta. Composite vector x tilde described using the shaping filter in a following form, and with regards to accepted notation for the nonlinear function f can be represented in a following form, where we use the Kronecker product, and remind you what the Kronecker product is. Thus, finally, we can formulate the goals of our presentation. First of all, we need to design an algorithm for polynomial filtering of the Markov sequence 4 using linear measurement 5. And we also want to illustrate its efficiency in comparison with the extended Kalman filter by solving a problem related to the processing of navigation information. Now I'm going to talk about the suboptimal algorithms, first of all about the polynomial filtering method. The polynomial algorithms are based on the assumption that the prediction probability density function can be approximated by Gaussian one. For the probability density function of the Gaussian random vector x, we use the following notation. As follow from the slide, the prediction density parameters can be determined as a h-tape according to the following expression for the estimate x and for the covariance matrix. It should be noted that the prediction parameters 6 and 7 can be calculated analytically if we take into account the polynomial form of the function f. And in the next slide, I will shortly explain how we can do it. Using known relation for the Gaussian vector z, we can rewrite the expressions 6 and 7 in a following form. The more details of this transformation you can find in our paper. Taking into consideration the above assumption about the Gaussian nature of the prediction density and the linearity of the measurements, the posteriori probability density function will be also Gaussian. Then, for the next measurement, the current estimate x and the current covariance matrix can be calculated as shown in this slide. Also, I want to say some words about the extended Kalman filter. To design extended Kalman filter, we use the linearized representation of the function f in the point that is the estimate of the estimated vector x from the previous step. This linearization allows us to rewrite expression for parameters of prediction density in a following form, and then the current estimate and current covariance matrix can be found as was shown in the previous slide. Now I'm going to explain the procedures which we use to estimate the efficiency of the filtering algorithm. When analyzing the efficiency of the algorithms, we will calculate the elements of the unconditional covariance matrix determined in two ways. Using the following formulas for real covariance matrix and for the calculated covariance matrix, where x, j, and y, j are samples of random sequences x and y. In the calculation unconditional covariance matrix, we use three algorithms. One of them is corresponding to the Monte Carlo method, the second corresponding to the extended Kalman filter, and third to the polynomial filtering method. And now I'm going to give you numerical examples. In the first example, I want to consider identification problem of the first order Markov processes That is often used in navigation to describe sensors arrows, sensors like gyros or accelerometers. In this Markov process X, the parameter theta is unknown and should be identified. Using the following composite vector, X theta, we can describe the random sequence in the following form. And now we can synthesize the polynomial filter, and also we synthesize the extended Kalman filter and the algorithm based on the Monte Carlo method. Next, we compared the three methods using the procedure described above. And the next slide, you can see the conditions at which the simulation was carried out. And now you can see the simulation results. As can be seen from the example, the accuracy of identifying the theta parameters and estimation of the sequence X by all three algorithms is approximately the same. Now I'm going to discuss example number 2, considering the random sequence, which shows the dependence of the gyro drift on the known temperature T. In this model, parameter alpha characterizes the gyroscope drift stability with time, and the parameter beta determines the effect of the temperature on it. Both parameters are unknown. Using the measurements obtained during the test, it is necessary to estimate the parameters alpha and beta. On the next slide, you can see the conditions of our simulation, and finally you can see the simulation result that the polynomial filter provides accuracy close to the Monte Carlo method and an appropriate calculated accuracy characteristic. As for extended Kalman filter, it allows significantly to the polynomial filter and does not provide appropriate accuracy characteristics. Now I'm going to conclusion. First of all, I want to mention that the polynomial filtering method has been designed, and it has been shown that the polynomial filter provides accuracy close to the potential accuracy calculated by the Monte Carlo method. However, the amount of computational required to the polynomial filter is much smaller than the amount of computation in Monte Carlo method. And also, the polynomial filter provides adequate calculated accuracy characteristic. Thank you. Thank you for your attention.
Thank you, Julia. Do we have any questions for this presentation?
Yes, I have a question.
Yes. Who's? Yes,
It's
Oleg.
me. Yes.
Yeah.
Good morning. Thank you for your presentation. I have some question. First, could you give any comments? Why does extended Kalman filter shows the worst result than other algorithms?
As I said in the presentation, in the when we use the extended Kalman filter, of course we use we linearize the function phi, which describes the behavior, dynamic behavior of our system. But when we use the polynomial filter, we didn't do it, and so thus we expect that the accuracy of the polynomial filter will be. Oh, sorry. Oh, yeah. Thank you. The accuracy will be that algorithm will be have more accuracy.
Okay, so because of linearization, yes?
Yes. First of all, because of linearization.
Okay.
Of the function thing.
Thank you. And the last question: what will be changed in the proposed algorithm if we deal with the polynomial order more than 2?
More than 2?
With high order polynomials.
First of all, if we unfortunately, I can't imagine the example of navigation data processing if this function could be described by polynomial more than two order. But if we find this example, maybe we can try it. But the idea of the algorithm will be the same, of course. We have to rewrite to present the function phi by the in the form of the some summons. And but in this case, of course, we will have the additional summons, and we have to write the parameters of the prediction density. In this, it's maybe can I answer to your question?
Yes.
Have I?
Thank you. Thank you very much.
Thank you for the question.
Do we have any other questions? Okay, I have a question as well, Julia. So in your presentation, you are assuming a first order extended Kalman filter, right?
Yeah.
So can you speculate how much you improve? Because as far as I understand in the slides, can we have the slides again of the presentation?
The first example, yeah?
Yes.
Yeah,
what happens if you have second, or I know there is also third order expansion for the extended Kalman filter. So what happens if you have higher order extended Kalman filter?
How higher? Sorry, I can't.
Yes, if you have, because here you have first order extended Kalman filter, you may have.
Yes, you're right. We have the sorry, I have something ring. Yes, here we consider the Kalman extended Kalman filter is a. Sorry, I can't. Only can hear the screen.
Yes,
it's correct. It's not extended Kalman filter. Sorry, it's our filter. Sorry, here we consider it only the extended. You're right. We consider the only. Sorry, maybe I can't get a question. You talk about the accuracy or about the advantages of the polynomial filter in comparison with the extended Kalman filter.
Yes.
Yes, but about this example, we haven't any advantages. You're absolutely right, but it depends on the example. But in the second example, we have it, and also we have another examples where we find them. This difference, I think it depends on the level of the nonlinearity of the function.
Yes, yes, correct. That's true. That's true. Thank you. You answered my question. So I will again give the pass to Oleg to proceed with the fourth presentation.
Okay, thank you. But we have, I think, approximately 2 minutes before the next presentation, and maybe Andrei Chiganov can say anything about the previous presentation, because as I know, this scientific area is close to your scientific interests. Andrei Chiganov, please.
Is he here? Yes.
Andrei Tsiganov is absent.
No, he's here. He's here.
He's here?
Yes. So let's unmute him. I can't unmute him. I don't know why. So where is he?
Okay, now the time for the next presentation, and I am pleased to present the paper with participation of our co-chairs, Fotios Stavrov. Are you welcome? Are you ready?
Hello, my name is Fotios Stavrou, and today I will present our work entitled Computation and System Identification of a Lower Bound on Scalar EQG Control via a Noisy Communication Link with Delayed Causal Side Information at the Decoder. This is a joint work with Mikael Skoglund. Both authors are with KTH Royal Institute of Technology in Sweden. In this slide, I give the problem statement. In particular, up left, we see a scalar value closed loop control system where between a stochastic linear time invariant plan driven by a Gaussian noise process and the controller intervenes a noisy communication link that consists of an encoder, an additive wide Gaussian noise channel with known capacity, and a minimum mean square error decoder, which is allowed to have a unit delay causal side information correlate to the data of the linear plant and driven by a Gaussian noise process. The goal is to minimize the linear quadratic cost. However, in this paper, we derive a lower bound on the steady state linear quadratic cost and the corresponding optimal linear time invariant policies. Although simplistic, when one extends our framework, in the multivariate case, the following motivating example applies. Consider the plant to model the dynamics of a leader drone in a swarm of drones. The decoder/tracker obtains the dynamics of the leader drone through a noisy communication link, and as a side information with some delay, the aggregated data of the position of the fleet via camera. The additional data received by the camera to the decoder serves as a side information in our system. The controller takes the information from the decoder and commands the fleet via the leader drone to move along a certain linear trajectory. A few words about the literature review. The precursor of this research direction without any causal side information of any kind was Tadigonda in 2004. In that paper, he derived sufficient conditions to ensure the separation principle, found analytically a lower bound on the scalar value case and showed that this bound can be achieved, found suboptimal lower bound in the multivariate case using a reverse water filling algorithm. Recently, this problem was revisited by Tanaka and his co-authors in two companion papers in which they derive numerically via semi-definite programming a lower bound for the multivariate Gaussian case and proposed an optimal realization of the encoding and decoding policies to achieve this lower bound. The optimal reverse water filling characterization was studied by Stavrou and his co-authors in 2018, and analytical solutions beyond scalar case are explored by the same authors. Achievability schemes for this problem are studied by a number of researchers. Some examples include Tanaka, Stavrou, Kina, and Kostina. General lower bounds beyond multivariate Gaussian processes and the refinement of the separation principle are studied by Kostina in 2019. The case of synchronized Gaussian causal side formation at the encoder and or the decoder is studied in Kostina and Stavrou independently. Throughout this paper, we assume that our encoder is linear. This means that the optimal controller is a certainty equivalence control law, and the control theoretic separation principle holds. The scalar valued version of the control theoretic separation principle is illustrated in formulas 2 to 5. I will only briefly discuss the cost of control in equation 5, because this is the important part of this paper. We see that the optimal cost consists of two parts. The first part is due to full state observation in our system, and the second part is the communication cost that stems from the fact that we have an encoder, a noisy channel, and a decoder. Tatikonda showed that the communication cost can be computed by a minimum mean square error state estimation problem by means of a sequential rate distortion function. The goal in such problems is to find the right sequential rate distortion function to minimize as much as possible the communication cost. Then, in order to show that these bounds are achievable, one needs to ensure that the rates operate at the channel capacity of the noisy channel. Since the separation principle applies under our assumptions, we will only consider the communication link in the closed loop system. We first use the following data processing inequality. In particular, the mutual information between the input to the channel to the output to the channel is always greater or equal to the causally conditioned delayed by one directed information from the input to the encoder to the output of the encoder. This inequality enables us to introduce a new sequential rate distortion function given in equation 6. This sequential rate distortion function is obtained in finite time horizon, but a simple adaptation of the data processing inequality implies that the channel capacity is always greater or equal to the steady state value of the sequential rate distortion function in equation 6. Now 6 has some nice properties. In particular, it's a convex optimization problem. And for the uncontrolled plan and the causal side deformation model of our setup, it can be shown that the optimal minimizer simplifies to one that only depends on the current input to the encoder. Additionally, if the uncontrolled plan and the causal side information are jointly Gaussian, then the joint process between these two and the output of the decoder is also jointly Gaussian. Under this assumption, we are able to characterize optimally the Gaussian sequential rate distortion function for our setup. This is given in formula 8, whereas the numerator of the logarithmic ratio of the objective is given in equation 9. Now, 8 is achieved by a conditionally Gaussian distribution that admits a linear Markov realization given in equation 10. This realization is non-trivial to be found and requires Kalman filter recursions, a solution of nonlinear equations, and mean square error estimation theory. The most challenging part is to find the deterministic coefficients in the innovation, HT, GT, and the variance of the independent Gaussian noise process. These values are given at the bottom of this slide. Now it can be shown that the steady state solution of the Gaussian sequential rate distortion function is lower bounded by equation 11. This statement can be shown by leveraging the concavity of the logarithm and Jensen's inequality. We have a few consequences that stem from this statement. First consequence is that one can achieve this steady state lower bound by fixing the distortion of the finite time horizon to be equal to the asymptotically average distortion at each time instant. A second consequence is that from consequence one, we can design the steady state variables of the optimal linear realization that achieves our optimization problem. And a third consequence is that from data processing theorem, the Gaussian channel capacity admits a further lower bound given by equation 11. In this slide, I compare our lower bound with known analytical steady state lower bounds on the optimal communication cost term. For the non-causal side deformation case, the bound is given in equation 12, and for the synchronized causal side deformation is given in equation 13. In the series of inequalities in equation 14, we see that our bound lies between these two bounds. This is because the synchronized causal side deformation always gives a better estimate at the decoder compared to our bound, and therefore it gives less smaller rates, whereas the non-causal side deformation case yields rates higher than our rate because the decoding policy is worse. All three bounds coincide if the coefficient in the realization of the causal side deformation is set to be equal to 0. At the bottom of this slide, we give a numerical experiment to show the relation between these three bounds for an unstable process. Interestingly, we see that although the non-causal side deformation is known to be to achieve rates that can never reach the absolute minimum, that is the log of the unstable eigenvalues, the bounds with causal side deformation have always a maximum distortion beyond which the rate is equal to 0. Note that from the series of inequalities in equation 14, one can dictate similar bounds for the linear quadratic cost. In this slide, I give the system identification for the optimal linear time invariant policies based on the optimal linear realization of our bound. To conclude, we derived an analytical solution on the communication cost that achieves a lower bound on the linear quadratic cost when the decoder in our system is allowed to have access to some delayed causal side deformation. We derive the optimal linear time invariant policies that achieve this lower bound. As an ongoing research, we will show that our bound is achievable. We will extend our framework to multivariate Gaussian and non-Gaussian processes and study noiseless channels instead of noisy. That was all. Thank you. Any questions?
Okay. Thank you very much for interesting presentation. Now the time for question. Are there any questions?
I can see one question by Andrei.
Andrei Matoren. Okay. Andrei,
yes,
please.
It's me once again. And my question is, can you mismatch it? Can you provide the example of causal side deformation? What is it exactly?
So I gave one, if you see the slides, I motivated the problem in the multivariate case, because here I only consider the simplistic scalar case to basically identify the policies in the system. But if you go to the multivariate case, the problem is much more difficult, but there you can find applications, because you can, for instance, see the side deformation, as I said, as a camera. Imagine that you have a room and you have some drones, and then you have a camera where this camera see the position or the direction of the fleet of drones, and sends data with some delay to the tracker or decoder. In my case, tracker is the decoder, who in turn sends the data to the centralized controller in order to inform, for instance, the drone to proceed to certain linear trajectory.
So it can be any additional information that we can obtain from external sensors that are not placed in the drones.
And it's,
and can we use this information in not centralized control, in other types of control? Not in a centralized control, but in decentralized.
So this is yes, I completely understand your question. Then the problem is it becomes much more challenging. You know, this area is quite active nowadays, because there is only, I mean, room for improvement so far, based on the control theoretic separation principle derived by Dadigonda back in 2004 for let's say MIMO closed loop system, centralized with centralized controller. So if you go to, let's say, distributed case, then you have an issue, because first you need to go again from at the beginning and derive separation principle, or see what are the conditions sufficient or necessary in order to achieve optimal or suboptimal or near optimal control policy. This is very, very critical. And at this point, we have no clue how this thing goes. We have no clue. We don't know.
Okay, thank you for an answer.
Okay. Are there any questions? I have a question. You say about unit delay.
Yes.
Unit delay. How many number of this delay can be in reality?
You can. This is a nice question. Thank you, Oleg. So here I used fixed. I assume fixed unit delay because I could, let's say, find explicitly analytical solutions. I'm an information theorist. I like analytical solutions. So if you deviate, if you go to more realistic scenarios, then you have to deviate as well from constant delays. You need to go to random delays. So then you have additional issues. You need to come up with alternative techniques. So I use here I use Kalman filtering and system identification and information theory. But you need to go beyond that. You need to come up with additional tools in order to understand how the delay affects the system in general, not the constant delay, the random delay. Now, if you go to the constant delay, here I assume delay 1, but you can have any number of fixed time delays, for instance, n time delay, and you can do this by simply assuming a state augmentation in the Kalman filtering recursions. So if you assume state augmentations, then you can incorporate in the big matrices the delay in the system. And you can find results, not optimally, but you can find nice results near optimal.
Okay, thank you very much once more for your presentation. And now time for the next paper. Fotios, you're welcome.
Thank you, Oleg. So we have our last presenter now, and it's the paper is entitled Automated Interceptor Guidance Based on Multiple Object Tracking, and the presenter is Mark Spiller.
Welcome to my presentation. My name is Mark Spiller, and I will talk about automated interceptor guidance based on multiple object tracking. Interception based on tracking requires correct target detection as well as correct association of pursuer and target objects. The tracking approach should be insensitive to clutter and should model the moving behavior of the targets correctly. In the past, Kalman filters and observers have been used to provide information about engagement-related data. However, mostly single target scenarios have been considered. In this work, I want to focus on a multiple target interception, and therefore I want to propose a multiple target interception system. This consists of detection of the targets, automatic initialization of the pursuing objects, tracking of all moving objects in parallel, and management of the target and pursuers. First, I will introduce into the problem of interceptor guidance. Then models for the moving behavior of the targets and the measurements will be discussed. After this, I will explain the mathematical background of recent probability hypothesis density filter. And after this, I will introduce the proposed multiple target interception system, and last, the performance will be evaluated. In the following, the engagement related parameters are discussed. We can see here a pursuer target pair. The pursuer is denoted by the red dot and the target is denoted by the green dot. 3 coordinate systems are introduced, the world coordinate system and 2 body fixed coordinate systems, C1 and C2. The body fixed coordinate systems have the origin at the center point of the pursuer. The x-axis of the C2 coordinate system is aligned with the LOS, the line of sight vector R. So the x-axis rotates with the LOS. The goal of the guidance is to minimize the distance between the pursuer and the target, so to minimize the length of the vector R. In the following, kinematic equations are derived in order to minimize the distance between the pursuing object and the target. The LOS vector R is differentiated 2 times using Euler's differentiation rule and expressed in coordinates of the coordinate system C2. Then, for the x-axis, the first differential equation is achieved, and for the y-axis, the second one. The velocity vector Vp of the pursuer is derivated once and expressed again in coordinates of the coordinate system C2. Then, the first equation is achieved for the x-axis and the second one for the y-axis. Finally, the acceleration of the pursuer can be replaced by the expressions given below. Regarding the differential equations, the distance r between pursuer and target is affected by the target acceleration, the velocity change of the pursuer, and the normal acceleration of the pursuer. In this work, the change of the velocity of the pursuer is assumed to be 0. The moving behavior of the pursuer can only be changed by the normal acceleration, which changes the moving direction of the pursuer. So finally, a nonlinear system is achieved where the input u is the normal acceleration of the pursuer. Then it can be shown that by driving this control variable to 0, the distance between the 2 objects will decrease. In this work, jump Markov systems are used to describe the moving behavior of the objects. This is advantageous because it can describe different moving behavior like straight ahead movement or turning maneuvers. Jump Markov systems can be described by a set of, in this case, linear stochastic systems, and each of this system corresponds to a mode. Then switching between these different system behaviors can appear, which is expressed by the mode transition probability, which has to be known before. The moving behavior of the objects is described based on a state vector which consists information about position and velocity in x and y direction. The measurements are radar-like measurements with information about range and bearing. The measurement model is nonlinear and a noise is assumed to be zero mean Gaussian white noise. There are non-target related measurements denoted as clutter. So the target originated measurements and in addition the clutter measurements form the set of the received measurements at time step k. The filter used in this work is based on a new kind of random variable called random finite set introduced by Mahler. A random finite set is a set of random vectors which has a cardinality that is also random. The random finite set can be described by a statistical moment called probability hypothesis density function. The PhD function V has a property that integrating over a subspace U of the state space gives the expected number of moving objects in this subspace. The PhD can be propagated through time using the PhD filter derived by Mahler. The PhD filter has an analytic solution if the intensity, so the PhD function, is modeled as a Gaussian mixture. This leads to the Gaussian mixture PhD filter, which is used in this work. In order to apply the Gaussian mixture PhD filter, a linear measurement model is required. To achieve a linear measurement model, the idea of converted measurement Kalman filter described in this paper is used. Based on the transformation, a linear measurement model can be obtained. The transformed new noise vector W is required to be zero mean. To achieve this, a debiasing factor is introduced, and also the noise covariance of the transformed noise can be expressed using these equations. To achieve automatic track initialization, two-point differencing method is used. The measurement set of current time step and previous time step are combined to form state estimations of potential new objects. State vectors with unrealistic velocities are disregarded directly. The remaining state estimations and the corresponding error covariances are used to add new Gaussians to the PhD function. In the following, the algorithm of multiple model GM-PhD filter proposed by Pasha is discussed. First, the Gaussians of the potential new objects are added to the a posteriori PhD. In the time update, the mean values are predicted to the next time step and jumping of the modes is considered. So the mode C' can jump to the mode C. This is also expressed in the equation by the first sum. In addition, the survival of the objects is considered based on the survival probability. So the weight of an object might decrease if it is not present in the surveillance region anymore. In the measurement update of GM-PhD filter, the first term describes that the moving object is not generating any measurements in the current time step based on the detection probability, and the second term describes that there are target originated measurements which can be used to update the Gaussian components, so the means and the covariances, which is further described in the next slide. So in this slide it can be seen that the mean values and covariances of the Gaussians are updated using the received measurements based on the Kalman filter equations. In addition, the weights are updated by considering the measurement likelihood. The GM-PhD filter is a combinatorial approach, which means that the number of Gaussians increases at each time step. This might lead to infeasibility of the algorithm. To avoid that, pruning is required. This can be done by merging Gaussians with low Mallah-Hanobis distance and by deleting Gaussians with low whites. So the whites indicate if a Gaussian is really describing a moving object. Consequently, the state extraction is achieved by considering high whites, which exceed a user-defined threshold. For these Gaussians, the mean values are extracted and form the state estimation of the objects, and also the indices of the Gaussians are saved in a set of indices. Track management is achieved by extending the work of Panda. The Gaussians are labeled using natural numbers. In the state extraction step, not only the state estimations are extracted, but also the labels. The labels form a set called the track list. For each track, the relevant informations are saved in a tuple. The tuple contains all the state estimations of previous time steps, the corresponding modes and time steps. In order to avoid initialization of two or more tracks describing one and the same object, the distance between already existing tracks and the potential new tracks is considered before establishing a new track. And also the length of the tracks is considered, so a track may never become active if the length is too short. This should avoid track initialization caused by outliers. And if an object is not generating measurements anymore, the related track is removed. To manage the targets, the track labels are divided into two sets, the pursuer list and the target list. The track list is used to update the pursuer and target list at each time step. Then, for each pursuer target peer, the relevant engagement-related parameters can be calculated. New targets are detected as track labels that are neither element of the pursuer nor of the target list. For each new target, a new pursuing object needs to be initialized. For the new pursuer, the initial heading angel needs to be calculated. This can be done based on the collision triangle equation. For the numerical simulation, a 10 by 10 kilometers surveillance region is considered. The target trajectories are predefined and independent of the moving behavior of the pursuers. Measurement noise with known standard deviations is considered, and also clutter is present. The moving behavior of the objects is described by three modes. The white noise acceleration model describes straight ahead movement, and the coordinate turn model describes turning maneuvers of the objects. Predefined angular velocities are used to make the coordinate turn model linear. Related to the control, the super twisting controller is used, and the controller parameters are tuned by trial and error. In the video, the object originated measurements are denoted by green dots and the clutter is denoted by black dots. The colored lines represent the detected tracks of the target interception system. The targets start in the right upper side of the figure, and it can be seen that each target is detected, and that for each target a pursuer is started which intercepts the target. On the right side, the misdistance of the target pursuer peers is visualized. The final misdistance over all target pursuer peers is approximately 42 meters. In this work, multi-target interception based on multiple object tracking is considered. An automated multi-target interception system has been proposed. The number of moving objects is not required to be known. The tracks of new objects are automatically initialized. The approach is applicable to nonlinear measurement models, and multiple modes to describe the moving behavior of the objects can be considered. Thank you for your attention, and I'm open for your questions.
Thank you for your. Oh, sorry.
Thank you, Mark, for the nice presentation. So do we have any questions? Yes, Roman, can you please put your camera on and ask the question? Thanks.
Okay. Can you hear me?
Yes.
Yeah. Thank you for presentation. Could I confirm some information? First of all, you showed the measurement model on one of the slides, and you show the results of your simulation. As I understood, the measurements were simulated. So how are you planning to make the measurements? I haven't caught up exactly. What kind of sensors do you want to use? Like, as I understood, you will explore 10 by 10 kilometers square, so it's quite big. And what kind of sensors are you planning to use to make measurements?
Yes, thank you for your question. In the work presented, we have this 10 by 10 kilometers surveillance region, and we have the origin, and at the origin, we place our sensor. And the sensor produces radar-like measurements, so we have information about the range and bearing. And normally, this is this produces a nonlinear measurement model. And in the work, we converted these measurements based on the idea of converted Kalman filter into a linear measurement model. Actually, it's a very good question, because the performance of the whole algorithm depends on the measurement and the accuracy of the measurements. So if we place our sensor at the origin, but the targets are very far away, that produces a large error in the position. So an optimization would be to place the sensor at the pursuing object so that that the range gets smaller if the pursuer approaches the target, and this will also produce smaller errors in the position of the measurements. But it's not implemented yet.
Okay, so, but I'm sorry, I haven't caught up exactly. I asked just about device. What kind of device do you see? In your paper, I read some information about radar-like sensor, and that's all the information. So you are planning to use something like radar-like sensor, as I understand.
Yeah, this was only a simulation, so we simulated all the measurements. But a similar real device would be, for example, a laser range sensor, just a laser range sensor that produces the range and bearing information.
Okay, I got. You are still working on this question.
Yes.
Okay, okay. And can I confirm one more question about data association? In general, I caught that you use Gaussian labels. So, but what the main criteria for comparing, for making some conclusions about data association? Is it distance, as I understand? You measure the distances, and you have some threshold, as I understand.
The data association is a general problem of the multiple object tracking.
Yeah.
And there are, of course, different methods, like the joint probabilistic data association approach, which is well known, but there are also some new works which are based on these stochastic variables, the random finite set. And so we use the filter derived by Mahler, and this filter automatically solves the data association problem So it evaluates the distances of the predicted position and the measured positions, and increases the weights. It increases the weights of Gaussian mixtures. So the weights are increased if the distance is small between the measured position and the predicted ones. So in our algorithm, we will get Gaussians with high weights that really correspond to real moving objects because the weights have been increased using the measurement likelihood. So that is why the algorithm itself solves the association problem, and we only need to consider the weights at the end that exceed a threshold, and then we will extract these mean values, which is the position of the estimation of the position of the object. Yeah.
Okay, thank you.
So we don't have time for another question. So with this, I would like to conclude this technical session of filtering. Thank you all the presenters for your nice presentations and the participants as well. Oleg, would you like to add something before we end up this session?
Okay, I also say thank you very much all participants, and I hope that maybe we can see each other in IFAC World Congress in Berlin. Do you know about the IFAC World Congress on control theory?
Yes, of course I know.
Maybe we can see each other on this scientific event. And I would like to say thanks for good collaboration, Fotis Stavrov also.
Thank you, Oleg. As far as I understand, we can discuss for another 19 minutes. So in that regard, maybe we should hear some of the presenters here that they have something to say. For instance, Yulia and Oleg Zaitsev. Let's hear Yulia first. Yulia, can you take the lead?
Yes, but sorry, I have a question for the last presenter. But now,
if it's here,
a question. But now, of course, I can say about this session. If you ask. Thank you. First of all, thank you for all participants, and it was a very interesting experience how to take part in this strange conference, because it's but on the other side it's interesting experience really, because we can maybe discuss the presentation more details in comparison with when we when we have a real conference, because we can study the papers before, because we can study the presentation before the conference, and so it was interesting. I think.
I actually agree with you on this issue. And I strongly believe that in the near future, virtual conferences will held much more often, because or maybe they can create hybrid conferences in terms of they both allow the real time presentation, whereas there is the possibility through some application like Zoom here to watch the presentation and presenter and be able to ask questions remotely. So in that regard, I think this is a nice feature, and definitely it will be incorporated in the near future in high quality conferences like European Control Conference. But you can actually ask Mark your question if
yeah.
doesn't
It was a question about the measurements which Mark used. Again, about measurements. Sorry. Have you ever considered this problem if you measure on the rank to the targets? Not the herring, on the rank.
Or only the range?
Yes, on the range.
Okay, I did not consider it yet.
But sorry, but as I have a question because I read the paper about. I'm sorry, I can't remember the author. I just remember the author this papers, but it was searching. They consider the problem by the range on the measure it on the range.
Yes. I'm not sure if this will be possible for the two-dimensional surveillance region, because that does really provide us observability of the whole state vector regarding x and y position and also velocity. If we only can measure the range, I'm not sure. I don't know if there is a paper. I can think about this problem. But if you only have, of course, then a one-dimensional surveillance region.
Yeah, as I remember, I don't remember the way how they do it. It was a quite complicated filter. This was consisting of the two parts. And the first part, they like you transfer the try to transfer the nonlinear measurement to the linear measurements. And during this part, they use of how I say they use only the rank measurements, and maybe they use a series of the measurements to get the one measurement of the position. As I remember.
Mm-hmm. Yeah, that might be possible. Or you could also try to use two sensors, of course. And if you only have the range information, you can combine both sensors. You will also get some information about the position. But I can check for this paper maybe and get some more ideas from it. Thank you.
Thank you, Julia. Thank you, Mark, for your detailed answer. So let's see if Oleg has still a question. Oleg Zaitsev, do you still have something to ask?
I also have a little question to Mark. Is it possible?
Yeah, definitely. We have time.
Okay. Thank you for your presentation. And the question is, as I understand, in presentation, you considered the flat scenario. And what about three-dimensional case?
Yeah, the three-dimensional case will require, of course, another sensor with more additional information about the position. And also we have to, we now considered a well-known sliding mode control approach to minimize the distance between the pursuer target peers, but this only works for two-dimensional plane. So the tracking approach itself is not a problem to apply it to the three-dimensional plane, because we only need to change the state vector and we need to change the measurement model to extend it to the three-dimensional plane. Mm-hmm. So the tracking is easy to extend, but I think we have to search for another control law that can also be applied then for the three-dimensional case, and think about the sensor. But the tracking itself can, from my point of view, easily be extended by just extending the state vector to the third dimension and changing the measurement model.
Mm-hmm. I see. Okay, thank you.
Thank you for your question.
Any other questions or comments related to the session? If not, I will say that we can conclude this this session. I don't know what. Let's see if the moderator has something else to say. But if there are no other comments, then I don't see the reason for keeping this technical session.
I think that everything is okay. Vladislav.
Yes.
We can finish.
Yes,
we can finish.
Yes.
Okay.
Great.
Goodbye, everybody. Thank you very much.
Thank you.
Health.
Thank you. Bye.
Mark Speller.